about the exam at all before I go into this stuff? We have a little time. No? And no questions? Or?
I mean, I don't really remember what I did or whatever.
Okay. Well, then let's continue. Actually, we've got some pretty interesting reactions we're about to happen upon. So, we've been talking about carbonyl chemistry so far. So we got up to imines and enamines. Let's kind of review some of the nucleophiles and stuff we have with carbonyl. So we've got, when I say, I'm just using a generic carbonyl here, meaning like a ketone, but also realize I'm also talking about aldehydes as well. So we used oxygen nucleophiles. So we used 2 equivalents of an alcohol in the presence of an acid catalyst while removing water. And we formed what kind of functional group from that? Yeah, acetals. Acetals. So let's draw an acetal out. You probably know what it looks like more than what it's called at this point. I'll put a little prime on the alcohol R to designate that it's different. Okay, and this was acetal formation. We also learned how to do a cyclic form of this. So, starting with ketone or aldehyde. You can use a diol, like a 1,2 or a 1,3 diol, in the presence of an acid catalyst, removing water, and cyclic acetal. And all these reactions are reversible. So if we want to go back from an acetal to a carbonyl compound, we would just treat this with acid, right? But what else would we have to add besides acid? Yeah, we'd have to add water instead of taking it away. That would reverse the reaction. So that's how you would put it on, take it off. So these are like protecting groups for the carbonyl. Okay, so that's oxygen nucleophiles. And then we looked at nitrogen nucleophiles, right? So we had carbonyl compounds reacting with primary amines. So that's a primary amine. And we needed an acid catalyst for this as well. And do we lose water in this reaction? Yeah, it's the same as before. That's what the acid catalyst is for. It's to make a good leaving group out of the carbonyl oxygen. So we would lose water in this. And what's the name of the functional group that we produce? An imine. So our carbonyl carbon is doubly bonded to a nitrogen that has an R group. And we call that an imine. And we also learned about using secondary amines. So before I stop, this is reversible as well, right? So how do we reverse the imine formation?
Acid and water?
Yeah, same conditions as acetal, just we add acid and water. And reverses. Okay. Now we learned enamine formation, which was just carbonyl compound. excess of this amine to make this happen. This is where you form an enamine. Now I probably should have put, other than an R group here, I might have probably been better to put in like a CH2R, because we're going to deprotonate that alpha proton, and we'll get something that looks like that. This is an enamine. Common mistake with that one is to sometimes make the double bond off the nitrogen R groups rather than the alpha position of the carbonyl. But I don't think anyone's made that mistake. It's just something I've seen in the past. So you always want to deprotonate, make the double bond from the carbonyl, not up here. Okay, so that's what we've studied so far. All right, what's the utility of this stuff? Well, we're going to learn when we study alpha carbon chemistry in the next chapter, the synthetic utility of these imines and enamines. For now, you just have to basically trust me that these are really important. But here we've already learned some really powerful synthetic tools with this. Right? These are great protecting groups. We're going to also see that they're central to the chemistry of carbohydrates. This is how disaccharides form from monosaccharides, and it's how glycolysis works on mechanisms of cleaving acetals. So this is central to biochemistry of carbohydrates. Okay, and we also looked at sulfur, or now we're going to look at sulfur nucleophiles. So this is like thiols. Thiol is a sulfur analog of an alcohol. The difference, of course, being that you have sulfur instead of an oxygen. And we can form thioacetals the same way we make an acetal, except that we use a thiol. And it's the same conditions. We have two equivalents of our thiol. Or if we want to make a cyclic thioacetal, we just use a 1,2 dithiol. Dithionenes, they're called. And we make these acetals under the same mechanism. Okay. Why does this matter? Well, let's look at the mechanism first, and then we're going to see why these are so cool, actually. So let's just go through the mechanism of how it forms. Let's use a cyclic example. Okay. So we're going to take this, and we have acid catalyst present. So the first step is a proton transfer to the carbonyl oxygen. And what do you think the next step is going to be? Yeah. We'll get a nucleophilic attack by the thiol at the carbonyl carbon, and then the pi bond will break, electrons going to the oxonium. And we make kind of our tetrahedral intermediate, and what's the next series of steps involved? Yeah, so we want to ultimately transfer a proton. Our goal here, where are we trying to get to, like, right now? We're trying to make a thioacetal, which is going to have the carbonyl, right? That's going to be bonded to 2 sulfur atoms, but right now it's bonded to an oxygen and a sulfur.
We want to make the OH group a good leaving group.
Yeah, so we need to make a good leaving group out of the water. And we'll do that by proton transferring. from the protonated thiol. So right now this is like a hemi-thioacetal in between an oxo and a thioacetal. So we'll just do a proton transfer. PT. Oops. And now we have water as a good leaving group, so we can cause it to leave by dropping down the electrons from sulfur, kicking off water. Now we can see that we can get a second intramolecular nucleophilic attack. And we have a 2-carbon bridge here, so we're going to have a 5-membered ring in total. We count up all the atoms we have. It's sulfur here, 1, then 2, and then 3, 4, 5. So there's a 5-membered ring from that. Okay. And one of our sulfur atoms is protonated still. So our final step would be loss of a proton. So this is catalytic with acid, just like the acetals. And that's how you make a cyclic thioacetal. Okay, so that's the mechanism. Any questions on how that works? Okay. So basically the same thing. Now, why do we care? Well, they're a lot more useful than just protecting groups. There are actually 2 big things you can do with them. One of them has to do with this funny sounding word, umpalung. Right? Now, umpalung is a new thing that you're going to learn now, starting now. And there are several versions of it. I think in this class, maybe we'll learn like 2 different ways of doing it. But there are a lot more in this. And you might remember when we were doing retrosynthesis, we came across a type of disconnection that I said was going to be especially challenging to do. And for that reason, it's a lot of fun. Because it's different. We're not used to doing it. Let's assign, remember how we were assigning negative charges and positive charges to a molecule? Let's do that here to this little carbonyl hydroxy system and see what we get. So what would the partial charge on this oxygen be? Oops, sorry. And then that makes the carbonyl carbon delta plus, right? And then what's the alpha? And then what's the hydroxyl group? Is that what it should be? No. What if, like for instance, what if I had drawn it, what if I had started at the other oxygen? then you get the exact opposite. So it doesn't make any sense, right? The natural polarity is off here. It's sort of like upside down, right? The natural polarity. And that's what the word Umpelung means. It means upside down, or inversion in German. It's a German word that means literally upside down. And so this is a difficult retrosynthesis disconnection. Like, we're going to see that, we call this dissonant. This is in contrast to something we've seen before called consonant. I'm going to sketch up here a consonant molecule. That's the normal order of things. And if you look at a huge rate, there's a ton of natural products, and you'll find this pattern put throughout them because enzymes naturally construct things in this way. But there are some other enzymes that construct them this way, in this dissonant pattern. And it becomes really necessary to be able to make things like this. Right? If our ultimate goal is to be able to harness the power of organic chemistry, we need to be able to set up molecules that have both of these patterns. Now, if you think about breaking this bond here and doing a retrosynthesis, where would you put the electrons from that bond? Well, you can think about a diradical there. That's one way of doing it. Otherwise, you have to take a side, right? And the carbonyl itself, the carbonyl carbon, we look at what a carbonyl is supposed to be. We should have a delta positive here. What we're going to learn how to do with thioacetals is invert that. We're going to learn how to make carbonyls nucleophiles. So we're going to do Umpelung, which involves making it this. And thioacetals are one way to do Umpelung. Another way we're going to learn in this chapter is something called cyanohydrins. And then there's another way, there's a reaction called the Stetter reaction. And we'll talk about carbenes maybe this semester. That's another way of doing it. But it's a useful technique because it allows us to change the reactivity of the carbonyl. So let's see, this is just background. This idea of Umpelung started coming, it's been around since about the 60s. I mean, people probably knew about it earlier than that, but really got formalized at C.J. Corey, who's got his ideas and everything, came up with, formalized the word, he called it symmetrization of reactivity, which is kind of a mouthful, doesn't really make a lot of, it does if you think about it in a certain way. We'll see that you can kind of think about it as, instead of symmetrization of a molecule, it's changing the reactivity so that you can make symmetric reactions, basically. And then this guy, Dave Evans, who came up with what we call the charge affinity inversion. It wasn't until Dieter Seebach kind of around the same time published a paper where we called it Umpelung, using a German word. He's a German guy, so it made sense. I mean, everyone uses it now. And I guess this is another way of pole reversal or inversion, the turning over of things. So it's a neat technique, and let's see how it actually works. So we have a thioacetal. Now, let's make a thioacetal from an aldehyde. And let's make a cyclic thioacetal. what do you know, what's the big thing about sulfur compared to oxygen?
Bigger, it's more electrons.
It's bigger, and it's got a bunch of electrons around it. So it's really polarizable. And it just so happens because sulfur is bigger and has a bunch of electrons around it, it turns out that this proton becomes suddenly acidic. It becomes an acidic proton, whereas in an acetal, it's not acidic at all. That has to do with the fact that electron density that ends up on this position, which was our carbonyl compound, can be delocalized into the orbitals around the sulfur and stabilizing it, kind of like hyperconjugation in reverse. Instead of stabilizing positive charges, it can stabilize the negative charges through polarizability. So what that means is we can actually deprotonate this, and it turns out we can use a base like an alkane base, N-butyl lithium, which you'll remember is just the lithium salt of butane. pK of butane is about 50. And this proton can be removed to give you an anion at what was the carbonyl carbon. So now we have a nucleophilic carbonyl compound. And we can react that with another carbonyl compound. So for example, we could take an aldehyde like, what's that aldehyde I just drew? Benzaldehyde. And it will act as a nucleophile with benzaldehyde. Now, if we did an aqueous workup with acid, we're going to accomplish two things. We'll protonate this oxygen, and we'll cleave the acetal. What will the acetal, the thioacetal, become when I remove the thiol? It'll become a carbonyl again, what it came from. So we're just reversing that process through the addition of water. So you protonate the sulfur, water, breaks the bond, water attacks, and ultimately you get a carbonyl back. And there, you just made a molecule that before was impossible. And this you can do on pretty complicated things. It's pretty neat. We're going to see another way of doing it later. I think on Friday we'll see cyanohydrins, the same idea. The idea here is to make the aldehyde proton more acidic. That's one way of doing it. The vitamin in your body that mediates this stuff, through a similar idea, it's called thiamine. But thiamine actually does umbilum in your body. We'll look at that maybe on Friday, actually. I'll have a chance to show you how it works with thiamine. Any questions on how that works? Okay, so that's umbilum with thioacetals. There's another reaction useful with thioacetals, and has to do with this stuff called Raney nickel. Not like it's Rainy, but it's named after this guy. His name is Murray Raney. He developed this. He was a mechanical engineer. I think this was in like the 1940s. He was working in a lab in industry, and they were working on hydrogenating vegetable oil for this industrial company. he was trying to come up with a better way to hydrogenate stuff. And started playing around with some metals and realized that if you took some aluminum in a basic solution of sodium hydroxide and water, he could actually produce a metal that would release hydrogen from it. It's these very small particles. It looks gray. You have to store it underwater. When it touches air, it actually explodes, but it's safe underwater. And it's little pieces of metal basically that have hydrogen stuck on them. And it's nice. You can weigh it out, and it just hydrogenates everything nearby. As long as you don't expose it to air. And it's called Raney nickel. And usually we just write it out. Raney nickel, like that. You don't really need to write the formula. Everyone knows kind of what you're talking about then. Raney nickel, it's essentially an H2 source. Okay. And what you can do with Raney nickel, I didn't have a slide for the reaction, is you can take a thioacetal. Sorry, I thought I made a slide for this. And it can have an RR or it can have an RH. It doesn't matter. If you treat it with Raney nickel, it's going to totally cleave off the thioacetal and give you an alkane. It'll deoxygenate or dethiolate, whatever you're thinking. So you can start with a carbonyl compound and deoxygenate it. So this is complementary to what other reaction that we've already learned.
We'll set it up before.
Yeah. I'm not even reading my own slides. The Wolff-Kishner. Well, how do we do the Wolff-Kishner again? What reagent do we use to initiate that thing? The conditions.
You're trying to do a amine and like a KOH and water.
Yep, those are the conditions. So we start with carbonyl and we end up with an alkane, just like this. That's why I say it's complementary. They do the same thing, just with different conditions. The conditions you use for Raney nickel for Wolff-Kishner, is you start with hydrazine, H2N, NH2. That's rocket fuel. And that's step one. It forms an imine-like structure, so you lose water. And step two is KOH and heat. And that was on the exam, I think. These basically do the same thing. Why do you think you would want to have these two options available to you? Why not just stick with the one Wolff-Kishner that came out first? Maybe competing. So what kind of competing reactions might we have? So we've got Raney nickel. What we do is we use acid, pure, and lose water. So the same conditions to make the intermediate that's deoxygenated, right? They're the same. But the difference is when you actually do the deoxygenation here. These are under basic conditions for Wolff-Kishner. Like you got to heat it with a really strong base. Is everything stable to bases, do you think? No, a lot of people will be incompatible with those conditions. Raney nickel, though, doesn't involve any bases. It's a hydrogen source. So it's pretty benign. On paper, this reaction looks great. In reality, it seldom works the way it's expected to. But on paper, it's fantastic. Okay. And not the last, but the last of the boring nucleophiles. Not really boring. The others were pretty. This is kind of boring enough. We've already learned hydrogen nucleophiles. This is really the same old thing. We're going to reduce. So we can think about hydride sources being nucleophilic sources of hydrogen atoms. And if we use lithium aluminum hydride, we'll get an alcohol. Or if we use sodium borohydride, we're going to get an alcohol. From a ketone. Will lithium aluminum hydride reduce esters? Which is the more powerful reducing agent? LAH or sodium borohydride. Yeah, this is stronger. This is a stronger hydride source. This is a weaker. So sodium borohydride, more selective. I.e., won't reduce esters. LH, not so selective. I.e., reduces esters. That's something I think maybe some people forget sometimes. So. Okay. Any questions on those? The mechanism is fairly simple. We've got carbonyl compound, a hydride source. The hydride has a lone pair of electrons on it. That's what makes it a hydride and negative charge. It attacks the carbonyl compound at the carbonyl carbon. The electrons move up. You work it up with H2O, and you get an alcohol. I think you guys completely understand that, though. That's pretty basic stuff. So, not as in pH basic, though. Okay, and let's see. We have quite a bit of time left, so we get to do some carbon nucleophiles. So the carbon nucleophiles are obviously the most interesting out of all of these because it lets us build in molecular complexity. What are some carbon nucleophiles that we already know about? What? I'm sorry, I couldn't hear you.
Grignard reagent.
We got the Grignard reagent. Yeah, that's a great one.
Deprotonated.
Like, for example, we've got a Grignard, we could say, like, we could use like a methyl Grignard as an example. And what was your second example?
Deprotonated alkyne.
Yeah, we could say alkanide. So if you take a terminal alkyne and you deprotonate it, you'll get an alkanide anion. Those are also carbon nucleophiles. So both of these we can use with our carbonyl derivatives to make carbon-carbon bonds. So let's do this example. This is a more sophisticated, similar to something I think we've seen. I took a molecule of this on the first example. So let's take a look. We've got a Grignard reagent here, and there's three equivalents. Why are there three equivalents present? How many functional groups are we going to add to here? Well, okay, so what three functional groups do we have to add to?
Yeah, so aldehyde.
We have an aldehyde, and this is an ester. So we can add how many equivalents to the aldehyde? We can add one equivalent. And we can add how many to the ester? Two equivalents. So that's a total of three equivalents are necessary to do this. So try to draw the product of this. get something different from that. Okay, so let's look at the mechanism for how that reacts with the ester. I'm gonna just, okay. Let's simplify it right now just by drawing that. Okay. So this is our ester, and we've got our Grignard reagent. I'm going to use an R Grignard. Okay. And we can just replace that with our R group when we go and redraw it. So what happens is the R attacks the carbonyl of the ester. And then this oxide anion kicks back down to reform a carbonyl. And what's the leaving group here?
On to the oxygen.
Yeah, we have to make this oxygen leave. That's the best leaving group out of the four of the tetrahedral intermediate. And then we have another equivalent of R. So if you go through the whole mechanism on that molecule, you'll end up with essentially what we had, which was if we tack on, it was at this position, let's see, yeah, it was over here. So over here we had our aldehyde. So that's going to have one of the R's attached to it as well. And that should be the template for your molecule, and you just replace R with Make sense? It's a little hard because it's a cyclic ester, which makes it a little tricky. It's easier when you don't have a cyclic one. It's kind of ugly, I think. I don't really like the look of the product. It's not really my style to draw products like that. It's too many things, it's like a tree. Too many branches. It's easy to make stupid mistakes. The most interesting molecules don't look like that. They're not big, like branchy trees. They have like small, compact, highly substituted structures. It's kind of what I like to draw. Any questions on any of this stuff? We did? At all, or anything? We have 5 minutes.
Unrelated question that I probably should remember. I don't remember, are negative charges like lone pairs on carbon, are they most stable at a tertiary point or a primary?
Okay, that's a good question. So are lone pairs more stable on a tertiary or not? So we know carbocations, right? We know that a carbocation stability is tertiary is the most stable, and then secondary and then primary most stable. Okay. And the reason for this stability is because the R groups are donating electron density into the carbonyl through hyperconjugation. So if we imagine a carboanion, do you think that these electrons want more electron density from R groups? No. And actually, there's also a hybridization thing. We have a carbanion, it can't be sp2 hybridized. Sorry, yeah, sp2 hybridized. It has to be sp3 hybridized. Because that's a lone pair of electrons, so it's pyramidalized. And it doesn't have an orbital for electron donation happen through hyperconjugation. And crowding it with a bunch of R groups just makes it more crowded. So you can imagine, let's look at a carbanion and imagine what the orbitals are like. You've got this is an sp3 orbital. One of these R groups. Now, are the electrons in this non-bonding sp3 orbital taking up more volume in their orbital when they're... The electrons take up more volume when they're bonded or when they're non-bonded? Yeah, when they're non-bonded. So it's squishing these R groups together more than an R group would. So that's another reason why it's unstable. So tertiary are a lot less stable. And probably the most unstable one that you run into is tert-butyl, like tert-butyl lithium, for instance. So you take a carbon, this is really basic. This stuff will ignite on contact with air.
I remember that. There was like a mechanism question or something on Live Plus that, I don't know, but something, the way it looked like the electrons had to move into a tertiary spot, and like, that's more unstable, maybe that's more stable, I don't know. I just got confused.
I could look at it. I'd be curious to see what that problem was. If you want to tell us next time or send me an email or something. So yeah, next time we'll learn a really new reaction called the Wittig. This stuff's cool, I'll just say, the Wittig reaction. Cooler than thioacetals by a long shot.